we've shown through the derivation of a Taylor expansion formula that we can express a function as an infinite summation of the derivative of the function, higher order of the derivative of the function. However, in the real world, people can't compute infinite amount of terms and sum them all up because computations have limits. So what people do instead is they approximate it using an nth degree polynomial, so centered at x0 minus x0 to the power of k over k factorial. That will give an incomplete expression of f of x, so we need to add the remainder, r sub n of x, and we'll call this p sub n x centered at x0 of x. So these formulas describe p n x0 of x and rn of x. We want to show an upper bound for rn of x. How do we do this? Well, first, since rn of x equals f of x minus pn x0 of x, we'll try to find a pattern. So the first thing we'll do is we're going to try to find how we can describe a constant, the error in the constant polynomial approximation. Or in other words, f of x minus a constant, so that's degree 0, so p0 x0 of x, and we want to describe this, and we're going to do it through an integral. So this, if you plug in n equals 0 into this formula, you'll get it equals just f prime, just f of x0. So the fundamental theorem of calculus tells us that we can write the difference between this as an integral from x0 to x of f prime of t dt. I'm going to rewrite this in blue to make it clear so we can keep track of everything we're doing. So again, it is the integral from x0 to x of f prime of t dt. Okay, good. Now let's do the linear polynomial approximation accuracy, okay, which is just f of x. Linear is degree 1, so minus p1 x0 of x. If you plug in 1 into this formula and then subtract that from f of x, you'll get f of x minus, and then this is going to be what you get from the formula, f of x0 plus f prime of x0 times x minus x0. Okay, now I'm going to distribute this to get f of x minus f of x0 minus f prime of x0 times x minus x0. Great, but from before, we know that this is just the integral from x0 to x of f prime of t dt. And then we still have this extra junk that we don't like. And we want to get all of this under one integral. So first, this might seem a bit counterintuitive, but we're going to take this part and apply integration by parts. So all of this is just going to equal, first, we take the integration of parts of this integral to get f prime of t times t from x0 to x minus the integral from x0 to x of t times f double prime of t dt, and then we still got to subtract this thing. Okay, now I'm going to expand the brackets to get, first you do x, so f prime of x minus f prime of x0 times x0 minus the integral from x0 to x of t f double prime t dt minus f prime of x0 times x minus x0. Great. Now I'm just going to bring this part forward, just rearranging the stuff in the equation, minus f prime x0, I'm going to bring it right here, x minus x0 minus f prime of x0 times x0, finally minus this integral again. So all I did was rearrange the parts of this equation. Okay, now I see f times x0 and f times x0. So I can just factor that part to get, not equal, minus f of x0, f prime of x0, I mean. And then it's just this stuff here minus, plus this. So plus x0. That actually cancels out. So we just get left with x. And then we can factor again, because this is times x. So we get x times f prime of x minus f prime of x naught minus the integral from x naught to x of t f double prime t dt. Okay, now we can rewrite this from the fundamental theorem of calculus as the integral, this was what we did before, from x naught to x of f double prime of t dt minus the integral of x naught from x naught to x of t f double prime t dt. Now, I'm just going to reintroduce the x because it's with respect to t, so times x. And then the bounds are the same. The bounds are the same, so we can just add them together to get from x0 to x of f double prime of tx minus f double prime of t dt. And then when you combine all of this, it just becomes from x naught to x of f double prime of t times x minus t dt. So I'm going to write that in blue. In blue, from x naught to x of x double prime, I think it'd be better if I switch the order actually. Sorry, x minus t times f double prime of t dt. So that was our linear polynomial approximation. Now, let's find the quadratic approximation. So, quadratic polynomial approximation, it's just going to be f of x minus p, quadratic is degree 2, of x. Right? So, if you plug in p into the formula, you're just going to get this stuff in the brackets, which is going to be f of x naught plus f prime of x naught times x minus x naught plus f double prime of x naught over x minus x naught squared over 2 factorial 2. Bam. So I'm going to rewrite this as f of x minus f of x plus f prime of x times x minus x naught minus this stuff right here. We know from before that this is just the same as the linear approximation of the function. So it's just this minus double prime x naught times x minus x naught squared all over 2. And then from before, we know that this just equals the integral from x naught to x of x minus t times f double prime t dt. And then we have all of this extra stuff right here. Okay, now, how can we get rid of this stuff and get the entire thing under one integral? Well, I'm going to do integration by parts on this integral right here, which will get me, you have to be careful here, because it's, here, let me show you, negative x minus t squared over 2 times f double prime of t from x naught to x minus the integral from x naught to x of minus 1 times x minus t squared over 2 f triple prime of t dt minus all that stuff here, so f prime, zoom back in, f double prime of x naught times x minus x naught squared all over 2. Okay, I got this because I just integration by parts. U will be f double prime of t, so du is f triple prime of t dt, so, and then I let dv equal x minus t dt, and if you integrate that with respect to t, you just get v equals negative x minus t squared over 2. Anyways, this, I can just cancel out the negative 1 and add the integral instead, and then let's just solve for this bracketed stuff. So, when you plug in x, it's just going to be x minus x something squared. So that's just going to be 0 squared, so this entire thing is going to be squared. So now we know that it's going to be negative. You plug in x naught into your value, so negative x minus x naught squared over 2 times the double derivative of f at x naught. And then I'm just going to rearrange this, so minus f double prime of x naught times x minus x naught squared all over 2, and then just plus that integral. So from x naught to x of x minus t squared over 2 times f triple prime of t dt. Okay, so notice that since it's negative, these just cancel each other out, and this is the same thing. This is f double prime of x naught times x minus x naught squared all over 2. So these just cancel each other out, and we're left with the integral from x naught to x of x minus t squared times f, the triple derivative of f at t all over 2 dt. Okay? So, now, what are our three integrals that we got? Our first one, for our linear approximation, was from x naught to x of f prime of t dt, right? Our next integral was from x naught to x of x minus t, I'm just going to write to the first power, times the double derivative of f at t dt. And then our third one was from x naught to x of x minus t squared over 2 times f triple prime of t dt. What do you notice from the linear approximation to the from the constant approximation to the linear approximation to the quadratic approximation? In all of these cases, we see the higher order derivatives, so the order of derivatives is increasing. We also see that the power that x minus t is raised to, here it's raised to the 0th, so it's just 1, here it's 1, here it's 2, and you might have also noticed that we're dividing by the derivatives. Here, we're dividing by 0 factorial, which just equals 1 by convention. Here we're dividing by 1 factorial, which equals 1, and then here we're dividing by 2 factorial, which equals 2. So, if this logic continues, we have a theorem. Taylor's remainder theorem. Remainder theorem states that if f of x, how do I word this? If the first n plus 1 derivatives exist at the point x naught, then we can say f of x equals the sum of from k equals 0 to n of the kth derivative of f at x naught times x minus x naught, because it's centered at x naught, all over k factorial plus this remainder, r sub n of x. And then the theorem states that r sub n of x is going to equal the integral from x naught to x, just like we had before, of x minus t raised to the n power, like we noticed that the powers were going up and up, times f of n, so the n plus 1th derivative of f of t dt all over n factorial. Some people take this and write 1 over n factorial. It doesn't really matter. So that's Taylor's remainder theorem. Next, okay, so this can't really be computed, but this is going to be able to help us determine an upper bound for the error. Now we want to solve for the upper bound of the absolute value of Rn of x, which will give us how far off or how good our approximation is, right? So right before, we just found that Rn of x is going to equal this entire thing, this giant integral. So it's going to equal from x naught to x of x minus t to the n over n factorial times f, the n plus 1 derivative of f at t dt. Okay, so there's one thing I gotta mention here. It's kind of intuitive, but it states that, let's do this in orange, the absolute value of the integral from a to b of f of x dx is always going to be less than or equal to the integral from a to b of the absolute value of f of x dx. Let me explain why this is intuitive. Let's say you have a graph, where f of x is an x, and then let's say you have, this is your function, and then this is going to be from a to b. So your positive area is going to be here, so you sum that up, and then you subtract your negative area from that. So if there's going to be some it dips below the x-axis and then goes above, there's going to be some canceling out that ultimately reduces the absolute value of the area. On the other hand, if you take the absolute value output of that function, so it's just going to look the same, except before it goes negative, it's just flipped on the other side, like that, and then you add up all the area, this is going to be greater than this area, intuitive. So, and it can be equal. That's why it's less than or equal to. So if we use this knowledge, we know that this Rn, the absolute value of R sub n of x, is going to be less than absolute value of this function, so it has to be less than from x naught to x of, I'm going to split up the absolute value across this function, so absolute value of x minus t to the power of n over n factorial times absolute value of f n plus 1 times t dt. Okay, so usually in practice, you're going to know what the n plus 1th, because you decide what n is, you're going to know what the n plus 1th derivative of your function is going to be. So let's just let b be the upper bound, so b for bound, hold on. So let's say you have an upper bound for this value, and we'll call that b. And this has to be true for all values in this integral, so for t between x naught and x. Right, so now I can take this b and rewrite it outside of the integral to get this. So x minus t to the power of n over n factorial dt. Okay, let me erase some stuff. Now there's two possibilities for the absolute value of x minus t. Either, let me draw a graph. Let's say in red is going to be the function we're trying to approximate. So, and then let's let this be x naught and this be x. Okay, and then let's let this green be our Taylor approximation of this value. So it's going to get really good at x naught, and then kind of like, let's say this, okay? So if x is to the right of x naught, that means that this area, this value is going to be positive. If it's to the left of x naught, the integral is kind of going to be reversed, so that it's going to be negative. So first, let's look at if x minus t, the absolute value, is positive, or x naught is less than x. If that's the case, we can just rewrite this in parentheses and then solve for that. To do this, let's make a substitution. Let u equal, sorry, it should be x minus t. Let u equal x minus t minus t. So this should be the same thing as b times the integral from x naught to x of u to the n over n factorial, and we want to find out what du is going to be. So let's just take the derivative with respect to t on both sides. Okay, so the derivative with respect to t of x minus t is going to just be the derivative of x with respect to t, so x is treated like a constant, so it's going to be 0 minus the derivative of t with respect to t is 1, so we have du over dt equals negative 1. Multiplying both sides by dt gives du equals negative dt. So I'm going to write du here, but bring the negative sign out to the negative b, to b. Great, now let's also change the bounds accordingly. So we have negative b times the integral of u to the n divided by n factorial du. So now our integral is in terms of u. So that means u should just be, so this is going to be x, but u is x minus t, so it's going to be x minus x, which equals 0. And then this is going to be u equals x minus t, so x minus x naught. So this is just the same thing as saying negative b times the integral from x minus x naught to 0 of u to the n over over n factorial du. Okay, great. This is actually an integral that we can solve with the power rule. So this is the same thing as negative b times the antiderivative of this, according to the power rule, is just u to the n plus 1 over n plus 1 factorial, over n plus 1 factorial, from the bounds x minus x naught to 0. Great. So this, I want to point out that this expression is going to be the negative of this when you substitute x minus x naught into u, because first you have to substitute 0 into this expression, and that's just going to make everything 0, minus this, so when you substitute it, you're just going to get negative b times negative x minus x naught of, so raised to the power of n plus 1 all over n plus 1 factorial, and then the negatives cancel each other out to give, if it's positive, b times x minus x naught n plus 1 all over n plus 1 factorial. Now, this is all under the assumption that x minus t is positive. What if it's negative? Then we can write this, instead of x minus t, we can write it as t minus x. So now u becomes t minus x. And then the derivative with respect to t of t minus x is actually just going to be 1 minus 0. So it's going to be positive 1. So du is going to equal positive dt. So that means there's going to be no need for the negative here, all the way down. It's all going to be positive. And then the bounds are actually going to become x minus x equals 0, but now it's x naught minus x. So it's going to be x naught minus x instead, x naught minus x. And then let's change it around the antiderivative to x naught minus x. And then when you substitute that in, you get x naught minus x. So you get b times x naught minus x. So that brings us to our theorem. I'm going to write it out. If Rn of x represents the accuracy of f of x, the accuracy of the approximation of f of x with an nth degree Taylor approximation. So that was our p n x naught of x degree Taylor approximation. And I'm going to write this in math terms. F of x equals the sum from k equals 0 to our nth degree Taylor approximation. So I'm writing the nth degree Taylor approximation right now. Kth derivative of f at x naught, centered at x naught, times x minus x naught to the power of k. Sorry, no. To the power of n. Sorry, to the power of k all over k factorial. Plus how far off we were, so Rn of x. Then the theorem states that Rn of x, or the absolute value for Rn of x, is gonna be less than or equal to b times the absolute value of x minus x naught raised to the n plus 1th power all over n plus 1 factorial. This is something you can calculate, and then you can get how good your approximation is if you have the degree of your approximation and where your approximation is centered. So that's it. Taylor approximations.